Hi everyone, welcome to this episode of Keipert Labs. Today we're going to be discussing series and parallel circuits. So we're going to be having a look at these two different types of electric circuits. We're going to define what we mean by each type, so what each label relates to, and then also some of the properties of both types of circuits, specifically focusing on current and voltage, seeing how they are similar and different. And then going to have a look at some applications or some uses for series and parallel circuits. All right, let's get started looking at series circuits. So here's a kind of a diagram or a schematic of a series electric circuit. So you can see over here we've got a battery or a power source and two light globes. Okay, so represented just with a simple picture and then with a schematic or a circuit diagram, our battery and our two globes. So you notice that both the globes, or each of the components, the parts of this circuit, are connected end to end. So this one to this one to this one and back again. Okay, so there's only one path, only that current can flow from here all the way around. And so all components must work for the electricity to flow, for that current to flow. We recognize that a circuit needs to be a closed loop, so that if there's a break at any point in this circuit, whether it's this globe is faulty or this one, or that there's a connection that's loose, then the current cannot flow at all. Okay, so that's one of the features of a series circuit. So if we have a look at now the properties of the series circuits, we're going to have a look at current first and then voltage. So here's a schematic of a different series circuit. This one's got a switch in it, but otherwise it's the same. So we've just got two globes in series. So what we notice for the current in a series circuit is that we have the same current for each globe, but that is which is equal to the total current. Okay, so the current, if we measure it at any of these points, so the current leading up to the first globe, the second globe, or at some other point in the circuit, all of those numbers are the same. Okay, but the idea with that is that the more globes that we have in our circuit, the smaller the overall current will be, because we've put more resistance in it. Each globe provides resistance. So when we're thinking about current as the rate of flow of charge, so how much charge is passing every second, when we have more points that it needs to slow down, then through the whole circuit it slows down. So the more globes we add, the lower that current ends up being. But the current at every place in the circuit is still the same. Then when we have a look at voltage, the total voltage in the circuit is equal to the sum of the voltage drops that we detect at different points in the circuit. Okay, so if we have a look, say, looking at the voltage that we have going into and then that drops across this globe. So the idea is that there's a certain amount of voltage going in, and then as it kind of goes through and past, that then we end up with a different voltage on the other side, and then the same thing over here. Okay, so the idea is that we start with the full amount of voltage that the circuit, that the power source can provide, and then it drops, and then it drops again. And so that the total voltage that's here is then spread out between those two globes. The more globes that we add, the smaller the voltage drop, or the smaller the voltage will be at each stage. So what we notice then is that each globe drops in its brightness. Okay, so the more globes you add, the dimmer they all are, because we've only got a certain amount of voltage that we can give out, and so it needs to be used up in a portion at each globe. Okay, now if we're having a look at a parallel circuit, okay, so we can see that we've got two light globes, but connected up not end to end this time, but they're connected up on separate paths. Okay, so it's like each globe has its own little circuit within the circuit. Okay, so that it can go from the battery to go through this one here, so kind of going around this sort of direction, or it can actually kind of go down and then through this sort of direction instead. Okay, so we have two separate paths, one for each globe. That means that we've got multiple paths that the current can flow. Okay, so thinking about like traffic, so the series circuit was like a one-lane highway, or even just one road heading from point A to point B. And therefore then whatever happens on that road is going to slow down or going to have an effect on the number of cars that can drive on it. But whereas when you've got multiple different roads that you can travel on to get from one destination to another, then that's going to influence how fast you can get there. Okay, because that means that if one component is broken or doesn't work, that the current can still flow. So for example, if this short circuit, if this one that's here is broken, that light globe is broken, then the second globe can still work because the charge can still flow around to that one. In the same way that if you've got two routes that you might drive to a particular place and one of them is blocked or there's a car accident, then you take the other one and you can get where you need to go. Okay, so now looking at our current and our voltage in parallel circuits instead. So what we notice is that the total current that we can get in that circuit is equal to the sum of the currents that we have going through each globe, individual globe, because when we have more paths we can take, we can pass more charge around that circuit per second because there's more than one place they can go. It's like if you go to the supermarket and they open up more checkouts, you get more people through in one go because each checkout can take more people, and so then you can clear the line faster, in principle anyway. And so the more that you have, so that then you can add those currents together and get a total current. So the more globes you add, the more current you have. You can have in that circuit. Each one is going to feel its own individual kind of current. It will be different at different points in the circuit, but the idea being that that's how it kind of works out. But then if we have a look at our voltage, that each globe experiences the same voltage drop, or the same, it experiences the same amount of voltage. So the voltage drop as we go through this globe is one value, which is the same as this one, because each one, and it's equal to the amount that actually comes out of the power pack to start with, because all of the energy from this power pack is going into this light globe because of that path, but also go into this one because of that path. So that's partly the other reason why the globes both are brighter in a parallel circuit than they would be in a series circuit. Not only because the current, you can get more current through, but because they're experiencing a larger amount of voltage at each globe. So more energy that's going in there. Okay, so more globes though means that there's no change in voltage, that the voltage is constant because it's the same as the amount that the power pack is giving out. You add more globes, that's not going to drop. It's not going to increase, but it's not going to decrease either. Okay, so thinking about how we might use series and parallel circuits, or when we might encounter them in everyday life. So series circuits would be kind of typical simple circuits. Perhaps an example like old-fashioned Christmas lights, not ones that you'd buy these days, but when they originally kind of came out, and that then everything was all connected up in one line. And if one globe broke or blew, that then the whole thing went out, and you had to have a devil of a time trying to figure out which one to replace. But we also see series circuits heading into appliances or in safety switches, or kind of setups to make certain appliances work. So that, starting a whippersnipper, and you kind of got to press multiple buttons, the switches are all in so that it travels all in one line so that it can't start accidentally or it can't start unintentionally. And so going into an appliance is a series circuit all in there because of the way that's designed. Whereas parallel circuits are more common in your household wiring, or wiring in a building, so that if one light globe goes out, you don't get zero power at all. You can just replace the globe you need. And more modern Christmas lights, for example, have parallel circuits so that only one bulb will go out if it stops working, and you can either replace it or you can just live with it. Okay, so we've talked about the definitions of series and parallel circuits, so in terms of connected end to end or in separate paths, and that their properties in terms of current and voltage are different. And then that leads to some different applications for both. All right, thanks very much for watching. Bye for now.